This is going to be CCNA 1, Chapter 4, Network Access Layer, that we're going to discuss in this video. Network Access Layer refers to the TCP/IP model. If you're looking to line that up with the OSI model, that would go over the physical and the data link layers in the OSI model. So that's what we'll be discussing: network media, data link layer protocols, media access control, so on and so forth. Okay, so the first section is on our physical layer protocols, and we're looking at the types of connections for your home router. That would be your home router is really like a router, switch, and wireless access point in one most of the time. So you've got your switch ports here, your Ethernet connection. You've got a wireless antenna in there for your wireless signal. It's just going to plug into your PC, whether it's a laptop or desktop, into that network interface card, your Ethernet network interface card, or you're going to connect to a wireless signal. What they have pointed out down here is just wireless range extenders, which will extend the range of your internet. Not the best devices in the world, from my experience. They will cut your signal's speed down by quite a significant amount. So I guess kind of use them at your own risk. I'd rather personally try a power line option, but range extenders are an option as well. Okay, the purpose of the physical layer. The purpose of the physical layer. If we look at the OSI model here, the application presentation, sending data on down as it's encapsulated and de-encapsulated. Down here with the physical layer, we are taking our data link frame and turning it into bits to send along our network media. So that's what the physical layer is doing, turning that frame into bits and sending along whatever media we have in use. That media could be copper cabling, it could be fiber optic, it could be wireless microwave signals. So that's kind of how you can tell what's a 1 and what's a 0 when you're using these signals. The copper cabling sends electrical signals, and the pattern of your electrical pulse is going to indicate a 1 or a 0. So if you're up here with that electrical pulse, you've got a 1. Anything down below a certain threshold is going to be registered as a 0. So those electrical pulses are what generate 1s and 0s. For your fiber optic, you've got patterns of light. Your light being on is a 1, your light being off is a 0. So that's what you have running in your fiber optic cabling. And then you have the pattern of microwave transitions, where you'd have above a certain threshold would be a 1, below a certain threshold would be a 0 in your microwave signals. So you can see how a digital signal would compare against the AM, FM, and PM signal with your microwave signals here. Okay. Physical layer standards and who governs them. They're implemented by these governing organizations: the ISO, the EIATIA, ITU, TNC, and IEEE. I'm going to go ahead and let you read about those. I think we had discussed in a previous chapter that IEEE and ISO are probably ones you want to remember. The IEEE develops Ethernet and wireless LAN standards along with Bluetooth. The ISO made up the OSI model. So those are ones you can concentrate on, but all of those are governing what we use in the physical layer. Okay. And we'll move to physical layer characteristics. Alright. So with Manchester encoding, you can read a bunch about it, but basically you get a 0 or a 1 based on voltage here. So if you have a transition that goes from low to high, based on this baseline here that we have going across the middle, you're going to get a 1 with Manchester encoding. If you have a transition from high to low, that's going to be a 0. So that's how your 0s and 1s are being generated, as a voltage transition from low to high for 1, or high to low for a 0. Your modulating waves are going to just modulate at a certain frequency to create 1s and 0s, whether that frequency is a little longer, a little shorter, okay, to create your 1s and 0s there. So it's the same type of concept, crossing a midpoint to create your 1s on the top section, zeros in the bottom section. And you can see how those things would look here. Bandwidth. Bandwidth is I guess you could say the optimal speed of your connection. What you have potential to reach based on the cabling that you're using, based on the devices that you're using. Usually measured in bits. When you're talking about speed, we typically measure in bits. When you're talking about storage space, you measure in bytes. So that's where some people get confused between bits and bytes. There's actually 8 bits in a byte. In byte, again, we use bytes when we're talking about hard drives and storage space and things of that nature. Bits when we talk about speed. So our speed, you've got your units of measurement, bits, kilobits, which is basically 1,000 bits, megabytes, which is 1,000 kilobits, megabits, which are 1,000 kilobits, gigabits, terabits, each 1,000 of the previous. We don't, well, I haven't seen any terabit speeds yet, but maybe someone has them. If they do, then good for them. But gigabit speed to 10 gigabit speed is typically all we see right now. Maybe terabits will become commonplace someday. And you can kind of just see the equivalency over here. So that's all about all I'll say on that. So you have your bandwidth, which is the speed of your cabling, the speed of your devices, what their potential is basically. If everything's in optimal conditions, your throughput is going to be the speed that you actually get over a period of time. That's what your throughput is. So even though you might have, in this case, maybe you're supposed to have a 100 megabit connection, but for some reason you're only getting 80 megabits a second. Whether there's interference, maybe whether you're sharing a line with somebody else so you don't have all the speed available to you. There could be all kinds of things that are happening. So your throughput is the actual speed that you get over a period of time. At home, if you want to test yours, there's a bunch of testing sites. It's just, if you type in speed test or internet speed test, you'll probably go to the site called Ookla. It'll give you a speed test and show you what your actual throughput is at home. Here we just have the different ports available to you on a Cisco router. I believe it's the 1941 router. You've got some fast Ethernet ports on it, SHDSL interface here. Your management ports like aux, and your 2 console for the console for USB, the console for your normal rollover cable. You got your gigabit Ethernet ports, and you have your USB Type A connectors, which could potentially be used to upgrade your firmware or something like that. Let's move forward. So network media, different types of cabling that we have to use on the network. So we're going to take a look at that next. First being copper cabling. So something we need to be concerned about with copper cabling is interference on your signal. If you have your signal, your cabling too close to, I don't know, power or lights, UV lights, there can be interference that occurs. So what you'd have basically is you got your pure digital signal here, which would look all nice and neat, and this isn't what your signal looks like with interference. This is actually what the interference is doing to the line itself. You mix those two together, you get something like this, and you're hoping that you don't have so much interference that one of these ones turns into a 0 or 0 turns into a 1, and the data you're sending across the network is corrupted, so to speak, or at least it's been altered. Okay, so what the computer reads is the interference plus the pure digital signal that you would see here. So if you have your signal running along with other lines, power, not UV lights but fluorescent lighting, you're going to end up with interference. There's also something called signal attenuation that can happen. So signal attenuation just means that the further a signal travels, it deteriorates, and that means it's going to be more susceptible to interference. Where these peaks are yay high up here, the further your signal travels, it's going to deteriorate. So maybe your peak's way down here, and this little bit of interference is going to turn a 1 into a 0 because the signals have run through too long of a cable, or it's just had that much time to deteriorate. So that's something that can happen with signal attenuation, which means that it has deteriorated over time. There's also something called crosstalk that can occur. That is when one wire inside your cable, the data on it interferes with another wire that's just adjacent to it. So there are measures that are taken to stop crosstalk from happening, but that is when the electric or magnetic fields of a signal on one wire cause the disturbance to a wire adjacent to it. Okay, so we'll move on to there. You've got a couple types of copper media. You have your unshielded twisted pair, which is our standard cabling, shielded twisted pair, and coaxial cabling. We mostly use in networking unshielded twisted pair. That's our most common cabling type, unless we know that we're going to be running cable in a place that's going to have some high interference, so we need to use that shielded twisted pair, or maybe even fiber optic. So the unshielded twisted pair, you have your outer jacket. This is just the casing. You've got your twisted pair wires in the middle, and they are twisted to protect the signal from interference, more specifically crosstalk. Okay, so that's how you're cabling your twisted pair cabling is protected from crosstalk. It's because we have those wires twisted together. They're color coded because when you are running cable yourself, you kind of need to know which cable is which as you're hooking up those cablings to the RJ45 head that you'll put on top of it. You need to know which cables are send cables and which cables are receive cables, so they're all color coded. Your shielded twisted pair, you're basically going to have a foil shield around an unshielded twisted pair cable. That's how it goes. In some shielded twisted pairs, you might even have some encasing around the wires themselves, but mostly it's going to be this foil shielding that you see here, that you saw back on this slide here. This foil is the shielding. Okay, so you've got that. And we got our coaxial cable with the outer jacket. We got our braided copper shielding, plastic casing, and then finally the little copper pin on the inside. Most common one that we're probably used to is the F-type, which you have on your cable boxes, or we've had on our cable boxes for the longest time. Then you have your N-types and your BNC type over there. So F-type is the more common one that you'd usually see. Okay, copper media safety. The separation of data and electrical power cabling must comply with safety codes. Yes, it must. Okay, cables must be connected correctly, hopefully. Yeah, I don't know if the colors mean anything, but usually the colored cables, if you're setting up a network, they will mean something, whether the cable is a crossover, a straight through, something like that. There's no set color scheme, but if you're designing a network, you probably are going to make the cable wires mean something. Installations must be inspected for damage. Yeah, and electrical equipment must be grounded correctly. Okay, so unshielded twisted pair cabling, properties of. Well, let's go ahead and move on to the different types we have of unshielded twisted pair. We have your category 3, which you would most often see for phone lines. You won't see it in your networks that you build. What you're going to be using is category 5E, most likely. You don't really see category 5 anymore. I guess you can still buy it, and if you accidentally buy category 5 instead of 5E, you might be wondering why your network's running so slow, and it's because you've got the slower cabling. 5E supports up to 1,000 megabits per second. 5 can technically, but it's not really stable at it. It's really rated at 100 megabits per second, so you're probably going to see slower network speeds if you accidentally get 5 instead of 5E. In fact, they really shouldn't even be selling 5V much anymore. I believe they're around the same price. The one that is a bit more expensive is Category 6 cabling, which is rated as 1,000 megabits per second up to 10 gigabits per second. But again, just like the Category 5, it's not recommended that you go all the way up to 10 gigabits per second. But if you want the fastest unshielded twisted pair, Category 6 is what you'll go with. It's still not going to be as expensive as fiber optic, so depending on what you're looking to do, you might go with Category 6. As far as physically, the only big difference, there's a little plastic tube on the inside of the Category 6 that you won't see in Category 5E, or Category 3 for that matter. Okay. So different type of connectors. We have our RG45 unshielded twisted pair plugs, and you have a socket which will have a punch down on it in the back. You use a punch tool to punch that down. Okay, so it's kind of like male and female end here. If you look in our classroom, we have in the racks a punch down panel with a bunch of these jacks in it. Okay. You have a bad connector down here, and you have a good connector. The good connector, because you're going to need to know, or at least it's good to know how to make one of these cables. You want to make sure when you're making one that you have the plastic shielding all the way inside the head before you crimp it down. If it's not, you got exposed wires. That's easily to be pulled out, and you can just ruin the cable that way. So this is going to be good. This is going to be not so good. Alright, you've got two different standards for making cables. At least the two different standards for how the wires are laid out. You've got this A standard and this B standard. And it actually ends up that if you're going to use one or the other, most people will use B. I'm told that, I don't know, the fidelity of it's a little bit better, but I don't see why it would be. But that's what I've been told. So if you're going to just do a straight through cable, it'd be both ends would be B on it. Okay, which means it's all the cables in the same place at both ends of the cable, and that's what you're going with. A crossover cable would be one end looks like this, and one end is like this. Okay, so basically what you see here is that your orange and your green wires are swapped, because you're going to send and receive data on your orange and your green. So let's say that both computers or both devices that you have are looking to receive data on lines 3 and 6. Okay, if you're listening on your computer for data that's being sent on 3 and 6, and the other computer is listening on 3 and 6 as well, okay, then well, you're not gonna. No one's gonna receive anything because you're both listening the whole time. You're just both listening. If you have the other end on one of the PCs with 1 and 2, okay, this green connects to 1 and 2, and 1 and 2 are sending, 3 and 6 are receiving, then you're going to be able to communicate with each other because you're listening on the same wire that the other device is sending on. Same thing over here. So if this device is sending on 1 and 2, this device is listening on 3 and 6, then it's going to need to be able to receive that data. So that's what a crossover cable is meant to do. And we need to know the purpose of a crossover cable, when we need them versus when we need a straight through cable. For testing purposes, really, most equipment today just has something called AutoSense that will go ahead and, if one's sending on one wire, it'll listen on the appropriate wire and vice versa. So you don't really need to worry. You could pretty much use a straight through cable for anything in most equipment, most modern equipment. But you may run into a few older devices at certain sites that do require a crossover, or do require a straight through, and it can be a big pain if you don't know why you're not transferring data correctly, and that's the reason why. So we'll talk a little bit more about that and which devices require a straight through versus a crossover in class, that is. So unshielded twisted pair testing parameters. You do have wire testers you can use. Your cable length is going to be important. Your signal loss due to attenuation. Your crosstalk, math of the wires. So We'll use a cable tester much like this to make sure our wiring is correct, but we won't really have anything to measure attenuation or anything like that. Okay, there is a recommended cable length that we'll talk about in just a second. All right, fiber optic cabling. Money is no object, so you decide to go fiber optic, which is, I mean, the best cabling you've got available. You have a send and receive on fiber optic, two different ends for send and receive when you use fiber optic cabling. Okay, and what is it composed of? You've got your outer jacket. You've got the strengthening material on the inside. You've got a buffer, a cladding, and finally the core where the light is transmitted. It's a little less flexible than your RJ45 or your copper cabling, but this cable is pretty much better in every way. We'll take a look at that in just a second. So single mode fiber optic, you've got smaller core, less dispersion, suited for long distance applications, uses lasers as the light source, commonly used with backbones, campus backbones for distances of several thousand meters. So this is going to be the longest running cable in terms of how far you can send a signal. So it's going to be a lot further. It's basically further than multimode, further than your copper cabling. This is what you use for the backbone of a network that requires a long distance to be covered. Okay, multimode is also another form of fiber optic cabling, but it has a thicker core in the middle, potentially higher transfer rates, more data can be sent because it is a bit thicker, but because it is thicker, the data kind of reflects off the inside of the cabling, which will make the signal loss greater, and therefore it can't run quite as far as single mode. So if you need to cover a greater distance, you'd go with single mode fiber optic versus multi-mode. But if it's shorter distance, you're probably going with multi-mode for the throughput. Okay, uses LEDs as a light source, commonly used with LANs or distances of a couple hundred meters within a campus network. Okay, we got our different types of connectors: ST, SC, LC, duplex mode LC. You got your ST, which is a straight tip connector, which was one of the first connector types used. It has like a twist on, twist off mechanism to it. You've got the SC, which is your subscriber connector, sometimes referred to as a square connector. It has a push-pull mechanism to go on and off. So twist, then push-pull here. You've got the LC, which is like the little version of the SC, basically. It's called a lucent connector, sometimes called little or local connector. And this is just a duplex mode version of that. So those are the different connector types that you have. Alright, there's the whole cord. We've got cable testing there. What's the advantages and disadvantages of copper versus fiber? So basically, the advantage and disadvantage is, well, fiber's better at everything, but costs more. That's it's harder to install. So basically, that's it. You can see that in the chart. I'll leave it here for a second. Hopefully, you had time to take that in. Moving on. Wireless media. Properties of wireless media. Okay. Let's go ahead and take a look. We got Wi-Fi, Bluetooth, WiMAX. Not so much WiMAX anymore, but Wi-Fi and Bluetooth will be around. So WiMAX was a competing technology to LTE and really didn't quite make it. So there's that. So we got wireless LANs, and that's it. Okay. Well, that's really not it. You want to know, let me just make sure that doesn't come up. Well, it doesn't. But so you want to know that Bluetooth is a 802.15 standard. Wi-Fi is a 802.11 standard. There's different types of Wi-Fi standards. There's 802.11 A, B, C. I'm sorry, not A, B, C. A, B, G, N, and AC. Those are your different Wi-Fi standards. The only one that's not compatible, or at least backwards compatible with the rest, is A. The rest of them are B, G, N, AC, all backwards compatible with each other. AC is the latest. It has different iterations. I've seen it go up to, they started out with AC 1300, then 1750, AC 1750, AC 2300. That's the last one I've seen. So those are your different Wi-Fi standards. I don't think that comes up in the test and beyond that. But know at least the standards, and that A is kind of the odd duck. It was the first one and isn't compatible with the rest. Is not compatible with the rest. Okay, so we got our data link layer protocols. The purpose of the data link layer. So what does the data link layer do? The data link layer allows the upper layers to access your network media and send data. It accepts your layer 3 packet and packages it into frames, adding a frame header and a frame trailer. It prepares the data for the physical network, which you see right there on the slide. It controls how data is placed and received on the media. Okay. It's responsible for exchanging frames between different nodes on a network or different end devices on a network. Also performs some error detection that we'll talk about in a little bit. So here we go. So the data link layer does add your MAC address data to the frame, I guess, as it creates the frame, it adds the MAC address data. So that's the destination NIC, and the source NIC would be the source MAC address, destination MAC address that you see here. Okay. This is all contained in the packet from layer 3. So the layer 2 data is the MAC addressing. All right. You've got two different sections of the data link layer: the MAC sublayer, which kind of communicates with the physical media, okay, and the LLC sublayer with communicates with the network media, or at least contains the network layer protocols that are being used in that current packet. So there is potential for the data link layer to send a frame with multiple network layer protocols in use. The LLC sublayer allows for that to happen. So again, the LLC sublayer communicates with the layer above the data link layer and contains what network protocol is currently in use. The MAC sublayer, it provides the data link layer addressing, so you're adding your MAC addresses there. That's easy to remember. Also is going to frame the data according to the protocol that's going to be used, whether it's Ethernet, Wi-Fi, whatever protocol is being used. So that's what you're doing. Basically, the MAC sublayer communicates with the physical layer, gets data kind of ready to be passed down there, and the LLC sublayer communicates with the network layer. Basically, contains the network protocol that is being used. Okay, so that's the two sections. Kind of know what they do. All right. So this is basically showing what we have kind of discussed before in class, that each device on the network accepts the frame, de-encapsulates the frame, puts a new frame on the packet, and then sends it on to the new device. So that frame will have to do with what type of media the frame is going to travel on, also changing the MAC address from the previous source and destination to the new source and destination. Okay, we talked about how the MAC address changes all the time. That's happening in the frame. So again, at each hop along the path, a device accepts the frame from a medium, de-encapsulates it, re-encaps the packet into a new frame, forwards the new frame to over the appropriate medium of that segment of the physical network. Okay, so that's again what's happening. Not too much more happening on this slide. There's the standards we talked about before, and we'll go down to the media access control sublayer. All right, and topologies. Yes, we need rules for how to share media, otherwise we have chaos and collisions and bad things happening all over the place. All right, so we're going to talk about those rules in just a minute. Physical and logical topologies. A physical topology is really just the arrangement of nodes and the physical connections between them. You don't have any internet addressing, you don't have any ports listed. You're just kind of laying out a general network map with the physical topology and saying what is where. It's a little different with your logical topology, which we have here. Your logical topology is going to show you the way a network transfers frames from one node to the next. So you've got all of your ports listed, you've got your networks listed. Okay, so everybody in this section is in that network here, the 10.0 network. You got the 11.0 network, 102.0, and you have all your cabling listed here. So you're really, like I said, shows you the way a network sends frames from one node to the next and labels all the ports and network addresses involved. All right, so that's what a logical topology is going to do. As we move along, WAN topologies. So our WAN topologies, you got point-to-point, hub and spoke, and full mesh, which is a more typical topology that we'll discuss here, at least in most networking situations, full mesh. Or hybrid, I guess. Hybrid was probably the most typical that you'll see, a combination of the three. Or four, as there is star topology and whatnot as well. So point-to-point topology. Point-to-point is very simple. It's just two nodes connected directly. For all intents and purposes, it could be a direct connection that's virtual or a physically direct connection. Because they are directly connected, the media access control protocol can be very simple. You don't need any special addressing in the frame because there's only one place it's going to go or another place that it's going to go. So usually the bit count of the address in a point-to-point frame is going to be lower than in other topologies. So because there's only two nodes, one on each side, the addressing can be very simple because there's really only going one place. Okay. So yeah, it just sends the frame along from one point to the other. There can be, as I was saying, more devices in the middle. It can be a virtual point-to-point. It's still a point-to-point connection, even if there are all these devices separating the two nodes, because if you've set up a virtual connection where you're only able to send from one device to the other, it's never going anywhere else, you're still in a point-to-point technology. You could do that through a VPN, which is actually pretty common technology to use. So point-to-point doesn't need to be directly connected to nodes. It can have multiple devices in between, like this layer 3 switch that we see here, router, and a couple other devices. Alright. So the big difference here, if you're on a virtual circuit, usually if this were a standard network, when you'd send a frame from this device to, let's say, this router here, your destination MAC address would usually be that router. Okay. When you're on a virtual circuit and it's a point-to-point connection, the MAC address destination is going to be the node over here, because that's really all that it's communicating with. It's not really paying attention to things in the middle. So it's going to send it just straight on across. The de-encapsulation is not going to take place, and it's just going to arrive over at the destination mode. Destination node, not mode, node. So that takes us to our LAN topologies, and I think that's where, yeah, a star is actually a LAN topology, not a WAN. So what I said before, I was mistaken. We had point-to-point, full mesh, and hub and spoke for WAN. WAN. For LAN, we have the star, the extended star, the bus, which is really not used too much, and the ring topology in our LAN topologies. Okay. we have half duplex versus full duplex, whether you can send or receive only one direction at a time, or send and receive at the same time. Okay, so hubs, and this is a good graphic because hubs are half duplex. They can only send or receive. Switches are full duplex. That allows them to send and receive data at the same time. So that's what full duplex is. So if we have a half duplex situation with a hub in the middle, there are some issues that can come about. You've got contention-based access. So everyone's trying to send data when they're ready in a contention-based environment. Okay, why that is not good is because you can have collisions exist. Somebody's sending at the same time. So maybe this computer's trying to send here, this computer's trying to send there at the same time. So this data packet moves up and over. This one moves around too, and they both collide somewhere in the middle. Okay, so collisions can occur, but there are techniques to try to avoid those collisions that we'll talk about in just a second. One of them is something called, actually this is controlled access, not contention based. So we'll talk about the contention based ones. Controlled access would be a token ring type of environment, which again doesn't really exist too much anymore because we do have full duplex switches typically in our networks. But you basically have a token that goes around your network, and your computer can only send when that token is at their network. So when it's your turn, you can send information. It's moving very quickly, this token, but your computer is only going to send when that token is at its station. Whoops. Okay. Okay, so back to contention-based and how you deal with it. You have contention-based. So basically, your PC is going to see if the line's free in CMSA CD, which is collision detection. So once you see that the line's free, then you're going to send your media along. So in this situation, you can see that the medium is available, so I'm going to send. All right, I have a frame to send, but I have to wait because I'm receiving a frame. I'm not just going to spit something out at the same time. So that collision detection is used with hubs. So you want to make sure you remember those together. Collision detection, CSMA CD, collision detection, that's hubs. Okay. And when you're using a hub, your data that you send gets spit out everywhere. A hub doesn't make a decision on where the frame goes. It just kind of broadcasts every frame. So if you receive a frame that's not for you, you will ignore it. If you have a frame to send, you will wait if you're receiving, because that's what you're going to do with collision detection. You're not going to be able to send unless that line is free. Okay. So by monitoring the line in the previous example, basically you are seeing in this example that if you are receiving a frame, you cannot send. Okay. You're not actually monitoring the line. You're just at your PC seeing that since I'm not receiving anything, then I can probably send. And if that just so happens to be at the same time as someone else, you're going to be able to detect that collision and wait and send again. Okay. Collision avoidance, this is where you're actually monitoring the line and seeing that a channel is available or unavailable in Wi-Fi. Okay. Or wireless, I should say. So wireless uses this collision avoidance, CSMA, CA, collision avoidance, and CSMA means carrier sense multiple access. Yeah, multi-access. So that's collision avoidance. Monitoring the line when it's free, I'll send. Collision detection, if I'm receiving, I cannot send. But if I'm not receiving, I can send, and if there's a collision, we're going to be able to detect it. Okay. The data link frame. All right. The frames have three basic parts: the header, the data, which is kind of just the packet, and the trailer. Okay. So you've got your packet data here. You got your header. and you got your trailer. So you have your frame start, which is some sequence of bits to indicate the frame start, your frame addressing, your type, your control. You've got some error correction detection that goes on here to make sure that the frame arrived intact. Okay, that's what the error detection does. And you have some bits for the frame stop. Alright, so layer 2 addressing, we've talked about how that works and how it jumps every time the MAC address changes from device to device. Alright, I think we're about done. Some different examples of layer 2 protocols: point-to-point, frame, White 0211 wireless frame, frame relay we'll talk about a lot later. And Ethernet, I believe, is in the next chapter. It's all Ethernet. So that's that. One other thing, the error detection here, you've got something called a frame check sequence that goes on there, and a cyclical redundancy check that basically checks to see that the bits of the frame at the destination match up with the bits in this error detection section. Okay, so if they don't match up exactly, the frame is going to get dropped because you know that the frame is inaccurate or inaccurate, incomplete, something like that. I don't know. It's the end of the video. But that's what this error detection does. Okay, it takes basically a map of the bits that are supposed to be in the frame, okay, which are contained in here, checks it against the actual frame that the destination is receiving, and if they don't match, then you know that the frame arrived corrupted in some way, and it's going to get dropped. That's what the error detection does here. Okay, so that's the end of all this. I'm going to go ahead and stop the video now. So that's chapter 4, network access layer.